Yeah.
Yeah. So, good morning, everyone. Welcome to the final day, session one of the faculty development program on nanostructures, nanomaterials, and smart materials. So, we have today Dr. MohammedAmir sir from IIT Mandi. He's a research scholar who is working on functionally graded materials with Dr. Talha. So welcome to the session, sir. On behalf of MLR Institute of Technology and the Department of Aeronautical Engineering, I warmly welcome you to the session.
Thank you.
Thank
Thank you.
you. Yes, sir.
So, shall I start?
Yes, sir, you can start.
Okay. Respected faculties, good morning to all of you. I am Dr. Mohammed Amir, and I am here to present my research on the structural analysis of the smart functionally graded cellular structures and nanostructures. I am associated with IIT Mandi. Here is my presentation outlines. First, I'll discuss about introduction of the functionally graded structures, then mathematical modeling, how to model different structures, including in various influencing parameters like thermal effect, geometric imperfections, material stochasticity, and piezoelectric effect. That's just electric effect of electric field. And then we will discuss about nanostructures, how it can be modeled using different theories, and then few results, and then concluding remarks. Basically, functionally graded structures are very useful in aerospace structures, and the smart material like piezoelectric material. The use of this particular material make structure useful, very useful. Like this structure, you can observe where the manual maintenance is not possible, and angle of operation means it is very critical to operate in adverse condition, and the structure is get deformed under severe environmental conditions, like there will be very high temperature when it is exposed to sun, and it's just antenna in aerospace, means in space. So there is one side is very hot and other side is very cold, and the use of piezoelectric material, we can manually operate from here because of actuating effect of the piezoelectric material. And the functionally graded materials like curved panels, the functionally graded materials can be also used in various aerospace structures, like uh, this uh, uh, this Chandrayaan, I think it's ISRO's project, and the functionally graded structure made of graded cellular core make it very useful, where the light means where we need very low weight and good strength, means very good specific strength and specific stiffness. So we can use this structure in aerospace industry also. For analyzing these type of complex structures and complex materials, we need to incorporate various influencing parameters like geometric imperfections. It's just distortion in the structure, unwanted distortion in the structure present. And it is another influencing parameter is environmental condition. That is when it is exposed to the atmosphere, when entering into the atmosphere, any plane or any object, it face very high temperature thermal environment condition. So it must be included in the structure so that we get more reliable structural response. And material stochasticity, when there is always there is a randomness in the structure, so we have also included randomness in the material properties only. And the effect of electric field, by incorporating all these influencing parameters within the kinematic model, we get more realistic and exact, means accurate structural response. What is the functionally graded material? Functionally graded materials are very advanced composite materials in which Either composition or microstructure varies locally during the manufacturing, due to which mechanical and thermal properties vary smoothly and continuously in the preferred directions. This gradation in the material properties reduces stress concentration, thermal stresses, residual stresses. What is the functionally graded material? Means here we are talking about the material. Basically, functionally graded materials are categorized into two groups. One is the functionally graded material due to variation in the composition, and another is variation in the uh, variation in the material properties due to variation in their microstructures. So for type 1, it's just variation in the composition. It's generally made of ceramic and metal. Sorry. So the functionally graded material made of material A and material B, it's just generally ceramic and metals. So it's the composition of their composition varies from one surface to another surface, and accordingly the material properties also varies in that particular direction. And the functionally graded structure or cellular structure, we can say, are the structure where the variation in the material properties is due to the variation in the microstructures. It's it is also available in the nature. Like we can observe the bamboo stick or bone or any even skin. These also have gradation in in the they have also gradation in the material properties. Like bone, when we observe from outside, it's hard, and when we go inside, it start becoming spongy. Application of the functionally graded structures. The functionally graded structures are very useful in various industrial applications like aerospace, nuclear reactor, medical applications, energy. The graded cellular structures, as I discussed earlier, it's very similar to bone. So it is very useful in case of artificial bones and dental cases. Like it can be used as a bone implant or dental teeth implant. And another feature, like the functionally graded material generally made of ceramic and metal, these type of materials or these type of structures can be very useful where it is exposed to the high thermal environment conditions, because the ceramic can withstand very high thermal environment condition, and metal and generally ceramic is brittle, and when it is mixed with the metal, and it will also provide as well as toughness. So these structure are very useful in aerospace applications where it is exposed to the high thermal environment conditions. It can be very useful for nuclear reactor walls, and many other applications like sports. Nowadays different building materials, sports, and sports goods are prepared of the functionally graded materials. Now, this is how we obtain the gradation in the material properties. For that, uh, here we are discussing about the functionally graded material made of ceramic and just a composition, means mixture of ceramic and metal. So here the effective material properties varies in the thickness direction only, and for that we consider a power law distribution. Here the volume fraction of the ceramic depends on the thickness coordinate z by h and index n. And by changing the value of n, means selecting the value of n, we get different volume fraction index of the means volume fraction of the ceramic. Since using the rule of mixture, means volume fraction of the ceramic plus volume fraction of the metal will be 1, and accordingly using the rule of mixture we get effective material properties of the structure like Young's modulus and density and other Poisson's ratio and any other means other mechanical properties. So Ez is equal to Ec minus Em into something volume fraction of the that is a component volume fraction of the ceramic, and plus Em. So here we can uh, choose value of the n for different materials. Like we select n is equal to 0, then it will purely behave as a ceramic materials. Like this component will become 0. This particular, by putting n is equal to 0, this becomes 1. And if em and em get cancelled, and it will purely act as a ceramic component. And by putting n is equal to infinity, we get the effective material property is very similar to the metal. By here we can observe that for n is equal to 1, it's just a straight line. But for different values of n, the effective material properties varies in the thickness direction. Now we are discussing about different type of another kind of functional graded structure, that generally it is called as cellular structure. So based on the open cell approach, we have obtained the effective material properties, how the material properties varies along the thickness direction. Here from this figure we can also observe, here the porosity means maximum pores available at the center, and the at the top and bottom surfaces are generally less porous. So the effective material properties obviously will reduce at the center maximum, and top and bottom surfaces will reduce
Hello. So,
the effective material properties can be obtained using this formula. And in our study, I have considered three different types of force distribution in the graded cellular structures. One is type 1, type 2, type 3, and type 4.
sir, we lost your connection.
Maximum porosity occurs at the center. So accordingly, if
Hello, sir, we are losing your voice in the middle.
hello,
Hello, sir, we are losing your
uh,
voice
uh,
in
uh,
the middle. Yeah.
okay, am I audible now?
Yes, sir. Yes, sir.
Okay, okay, ma'am. Then in case of type 1 distribution, the effective material properties are minimum at the center because it has maximum porosity at the center. And for the type 2, it's in this case the maximum porosity occurs at the bottom surface, so the effective material properties varies accordingly. In third case, it's uniform distribution, means the pores are uniformly distributed throughout the structure, so effective material properties have nearly constant values. Now moving to the modeling of the various influencing parameters, like geometric imperfection, thermal environment condition, and other other influencing parameters. First, I will discuss about initial geometric imperfections. What are these? These can be observed from this figure. What we expected, we expect flat plate, but we get some sort of distortion in that structure. So we have to consider these distortions. These are unavoidable because of it occurs during the manufacturing process. The functionally graded materials manufactured at the high thermal environment conditions, at high temperature, and it is suddenly cooled to the room temperature. Then there is a very high chance to get distortion in the structure. So these are unavoidable uh, conditions, like geometric imperfection. So to model these type of imperfections, we have very generic function, which is w bar is equal to some equations. So here in this equation, we observe that eta is a maximum amplitude, imperfection amplitude, and h is the thickness of the uh, structure. And this whole function depends on the various constants like delta 1, delta 2, phi 1, phi 2, and A and B. A and B are the dimensions along the of the structure. Like it's just plate, then it's one side is A and another side is B. By putting suitable values of the delta 1, delta 2, phi 1 and phi 2, we get different types of imperfections. In this case, I have categorized the imperfections in three categories: sign type imperfection, and global type, and then another is local type. By selecting different values of constants delta 1, delta 2, phi 1, phi 2, mu 1, mu 2, we get different shape. These shapes are presented here. These are mostly exaggerated views of distortions, and these from this we can see it's sinusoidally distributed along the structure. And global type imperfections are globally distributed throughout the structure. In case of local type L1, L2, L3, it's locally occurs in any place. And suitably we can select the values of those constants, we get desired shape. Here, thermal environment condition. So, in my study, I have included temperature dependent material properties. How we can obtain the temperature dependent material properties BZ? Its equation is given by Reddy and Chen in 1998. For different values like P naught, P and P1, P2, and P3, we obtained these constants from the given table. And the temperature dependent means the value of the temperature, like T. We have considered two models, like distribution of the temperature in the structure. We have used two types of distributions. Like one is uniform distribution, means it's just assumption, means uh, temperature of the whole structure is constant. Another case, it's linear temperature rise, means one surface has higher temperature and another is at the lower temperature, and the temperature is uniformly, means linearly varying from top surface to bottom surface. By these are the constant P1, P naught, P2, and P3. These constants are available in the literature, so we get these values from the literature. And now moving to the mathematical formulation. For this, I have selected very simplified structure. It is just a curved beam, and for this, we have presented the displacement field. The displacement field is based on Reddy's higher order shear deformation theory, where by incorporating the C naught continuity, means the W and del W by del Z is we have considered independent degrees of freedom. So in this case, we have assumed theta is equal to del W by del Z, and this is the strain displacement relation for the curved beam. I have also included Lam's parameter, which is taking care of the uh, nature of the curved beam, and as well as it also covers the thin to thick beam. Means this formulation is useful, means can be applied on thick as well as thin structures. Now moving to the slide where we have used the smart material. We are using the function a smart material structure. So in this case, I have used piezoelectric material. So the constitutive relationship for the piezoelectric material is presented here. Here we can observe that stress is also depends upon the electric field, applied electric field. So when we apply the electric field, it's stress in the structure also changes. We can observe from these figures. In these case, when we apply the electric field, the structure is also get deformed accordingly. Now, how we obtain the elements of the electric field means, in this case we have a small assumption. uh, in this case, we assume that only z direction, means transverse direction electric field dominates, and other two in plane to other in plane electric fields, like in x and y direction, it is assumed to be zero. And how electric field is obtained? It's gradation, means gradation of the electric potential. So V is a here V is a applied voltage, means potential difference, and Z HP is the thickness of the piezoelectric layer. For an analysis, I have used solution this functionally graded. I have considered solution methodology as a means finite element method as a solution methodology. In this case, I have considered three noded beam element in where there are 4 degrees of freedom at each node, and the shape functions are written here. And I am considering all variables are P not continuous. This is the string energy equation structure, smart B, and another is kinetic energy. And using the variational principle, which is modified variational principle, the elemental free vibration equation for the curved beam, and by assembling all elemental matrices, we get global finite element equation. These are the boundary conditions considered to solve the governing equations. Now, moving to the nanostructures. What are the nanostructures? The nanostructures uh, are the structures where the at least one of their dimension is in nanometers, varies from 1 to 100 nanometers. These are classified in three categories, like one dimensional nanostructures, 2D and 3D nanostructures. Why they are useful? Because they have outstanding physical, chemical, and mechanical properties, and they have high surface to volume ratio. Because of these are very useful in various structures, means various applications. They have various applications in various fields. Materials are light, stronger, and they are durable, and they are also resistant to extreme load conditions. And we observed from the previous data, the NASA nanotechnology funding in 2002, it's around $46 million budget, and all of them means this amount is divided in four categories, like development of new materials, and sensors, and other components, electronic uh, things, electronics and data processing, and other basic research. It's it's almost very significant uh, contribution of the total budget. Means the nanotechnology uh, research is contributing a lot in their overall research. And other applications for the nanostructures, like it can be used as a nanosensor, uh, the reinforced composites, like graphene platelets and carbon nanotubes. These carbon nanotubes and graphene platelets are added to the composite, make them more strength and more stable, and even without increasing significant weight. So their weight is not increasing too much, but strength is increasing. So these type of reinforced composites are nowadays are very useful for the aerospace applications. And many other applications of the nanostructures are energy harvesting, probe, in tissue engineering, and drug delivery. To model nanostructures, uh, basically it is not uh, means it cannot be analyzed, or when it is analyzed using classical methods, it is not giving accurate answer when we compare with the experimental results. For that case, uh, these means modeling of these nanostructures have to consider using some modified theories like non-local elasticity theory, strain gradient theory, stress gradient theory, and many other modified theories, because it is not giving accurate results for the classical theories available in the literature. In my case, I have considered analytical method, which is based on non-local elasticity theory. How non-local elasticity theory came into existence? In 1972, Erigan and Edelin proposed non-local elasticity theory, which is based on different integral partial differential equation, and it was very tough to solve this equation. So in 1983, Aragon proposed another theory, means modified their theory to avoid complexity associated with the integral partial differential equation. In this case, in this theory, he has only differential equation term, where the mu is a constant non-local parameter which depends upon the material as well as geometry. And the modeling of the nanostructures is very similar to the classical formulation, means classical beams, like classical beam theories, like it is also we are also using higher order shear deformation theory, where it is higher order shear deformation theory. But only the difference is in the constitutive relation, where the in that case the constitutive relation was, means stress is directly related to strain. But in this case, non-local uh, theory, the constitutive relation is depending upon non-local parameters as well as their derivative, means derivative of the stress component. Now moving to the results, I have presented few results. First, I will present the vibration analysis of the graded cellular beams. Basically, beams, I have considered the curved beam in this analysis, and here I have presented the result for the curved beam, which is made of isotropic material, and its boundary condition is clamped. Opening angle is 120. Radius of curvature is 1 meter, and thickness and width and span, all geometric properties are given here. And we observed that, and we observed approximate method, that is finite element method. So we have to check the convergence first. So by increasing the number of elements in the study, we get converged result. And we compared with the reference results, and these reference results are based on analytical results. So we found that there is a good agreement between the results. And one more thing, first I would like to discuss the curved beam structure. Uh, I think is it visible to at the top place? It's there is a curved beam.
Yes, sir. Yes, yes.
Then the curved beam is have few parameters like it has opening angle, and it has radius of curvature, and span length is length L is the product of opening angle theta and uh, effective radius of the curvature, and H is a thickness. Whenever we are discussing about opening angle, means its span is increasing. Radius is constant, then its span is increasing by increasing the opening angle. So here the can I hello ma'am, can I minimize the top
Sir?
screen?
Oh,
It's not visible to me. What is written on the on the top?
yeah, you can, sir. You can. Like, just come out of this option.
Where?
Slideshow escape, you can press it. You can just
Okay.
close the slideshow, sir. Yeah.
It's sorry ma'am.
Yeah, you can now increase the size, zoom in, sir. Zoom in.
Okay. Simply zoom in.
Simply zoom in, that same screen is visible. And yeah, you can move to the side and close this slides outline to the left. Yeah, we can close it and zoom in. Yeah.
Is it visible to?
Yes, sir, it is visible.
Okay, ma'am. Thank you, ma'am.
Yes, sir.
Here the convergence and comparison for the frequency parameter, that is lambda, of the functionally graded curved beam is presented. In this case, I have considered three different types of material porosity distributions. This is graded cellular structure. In this case, we have considered three different types of porosity distributions, and the effective material properties taken are E1 is equal to 70 GPa, and density is 2702, means kilogram per meter cube, and its Poisson's ratio is 0.33. And the boundary condition means geometric properties like boundary condition, length, width, and opening angle is given. What is the porosity coefficient? It is the measure of overall pores volume fraction of the pores available in the structure. Its E naught is considered here as zero point 0.6. Here, here another convergence study. In this case, the number of elements are increasing up to the 20. We get a converged result at the number of elements 20. Hello, hello.
Yes, sir.
I think your mic is open, so
Okay, I
kindly
am
mute.
closing.
Okay, thank you, ma'am. Okay. From the, from this particular convergence and comparison study, we found our model is very efficient model, and it is giving converged result at the number of elements 20. And we found there is a good agreement between the results, means there is a very small difference uh, at n is equal, means number of element is equal to 20. It gives very close result. And here another here we observe the influence of the h by l ratio, that is thickness to length ratio, and the boundary conditions on the frequency parameter of the graded cellular curved beam. Here we consider the porosity coefficient E naught is equal to zero point 0.6, and material properties are as this taken earlier, and the boundary condition is clamped, and the opening angle is 120 degree. Here in this particular result, I have considered three different types of porosity distributions: type 1, type 2, and type 3. And we compare, here result is presented for the various porosity coefficients like 0.2 and zero point 0.4, and thickness to length ratio, point 0.02, zero point 0.05, and zero point 0.1. We observed that on increasing the H by L ratio from 0.2, 0.02 to 0.1, the frequency parameter also increases with the increase in the curvature, means thickness to length ratio, means uh, and of course this increasing the porosity coefficient, the effective material, means the frequency parameter depends upon the type of porosity distribution used. It will, I will explain you later. Like here, the effect of opening angle and boundary conditions on the functional frequency response of the functionally graded curved beam. Here we found that the material properties are given here, and boundary condition is clamped free, and simply supported. And thickness to length ratio is 0.02, and E naught is just a porosity coefficient. E naught is zero point 0.8 is considered here. Here, three different types of porosity distributions are also considered, and the frequency parameter for non-dimensionalized, means dimensionless parameter, is taken as omega L square by H under root rho 1 by E1. So we found that the effect of opening angle, means the graph is plotted against the frequency parameter versus opening angle. On increasing the opening angle, the frequency parameter is decreasing for the clamp and simply supported boundary conditions, while in case of clamp free boundary condition, it is increasing. Means it can be concluded that the effect of opening angle also depends upon the type of boundary condition used. Here, the effect of porosity coefficient, as I discussed earlier, and the boundary condition on the frequency parameter of the functionally graded curved beam. Here also, I have also considered three different types of porosity distribution for the graded cellular structure: type 1, type 2, and type 3. And the geometric and material properties are given here, and opening angle is just 120 degree, and non-dimensionalized parameters are also taken here. And we found that the on increasing the porosity coefficient, the type 1 is the frequency parameter increases for the type 1, but for type 2 and type 3 it is decreasing. Means it can be calculated that the effect of porosity coefficient is depends on the type of porosity distribution taken. And in case of type 3, it is giving maximum effect on the higher values of porosity coefficient E naught. Let's say at zero point 0.8, it is giving maximum deviation from the standard one. Now moving to the vibration analysis of the sandwich structures with a graded cellular structure, graded cellular core. In this case, uh, we have considered the sandwich structures. The sandwich structures generally have phase sheets and the core. In this case, I have considered phase sheets as a isotropic and constant material. Isotropic material, they have constant material properties, but in case of core, it has graded material properties. Here the previously defined three types of porosity distributions are considered for the core only, and the top and bottom phase sheets are constant. Here, the convergence study for the frequency parameter of the straight sandwich beam is presented because the curved sandwich beam results are not available in the literature. So I have compared with the straight beam results. So for the obtaining the results for the straight beam, we just put radius of the curvature r is equal to infinity. We get the results for the straight beam. For the sandwich beam, there is a very useful parameter which is thickness proportion. The thickness of the face sheets and the thickness of the core are and the thickness of the lower face sheet. So the proportion of the thickness is 1 is to 10 is to 1. This particular proportion of the thickness is considered throughout the study. So we compared our results with the reference result. We found that there is a good agreement between the results, and even for the straight beam, it is giving more converged means earlier convergence, like it's converged at total number of elements 12. Here the convergence study is presented for the isotropic material, that is the core is considered to be isotropic material, uh, means overall structure is isotropic, and the proportion of the thickness is 1 is to 27.7 is to 1, as taken by Ahmed in 1971. And the material properties and the other geometric parameters are given, and the boundary condition is clamped means it is fully clamped, uh, and the natural frequencies in is calculated in hertz, and the first mode and second mode, all these two modes are compared, and we found there is a good agreement between the result as well as the for the isotropic beam, it is converging at number of element is equal to 40. Now, the effect of distribution types and boundary conditions is observed for the this sandwich curve beam. Here we have considered two types of boundary conditions: clamp free and fully clamped. And by increasing the porosity coefficient e naught, the effect of these this uh, these porosity distributions also governs the means also affect the frequency response of the structure. Let's say on increasing the porosity coefficient for the type 1, it is increasing, but for type 2 and type 3, on increasing the porosity coefficient, the frequency parameter is decreasing for clamped free as well as cantilever, fully clamped and cantilever beams. Here, the effect of opening angle and boundary condition for the sandwich arc is presented. Here, I have considered the proportion thickness 1 is to 10 is to 1, and uh, three types of porosity distribution, like type 1, type 2, and type 3. And we found here, as we discussed earlier, uh, the effect of opening angle depends upon the type of boundary condition used. Here, the effect of thickness to length ratio h by l and boundary conditions on the frequency response of the sandwich arc. Here, I have considered opening angle theta is equal to 90 degree, and other parameters are given. By increasing the thickness to length ratio, the frequency parameter is decreasing irrespective of the boundary condition type. And by increasing the thickness to length ratio, it is changing from thick structure to the thin structure. Let's say by decreasing the thickness, by keeping length constant, by decreasing the thickness, its S by L ratio is decreasing. So in that case, the frequency parameter is getting higher and higher. So it can be conclude that the the frequency parameter is higher for the thin structures, thin sandwich arc than a thick structure. Now the free vibration analysis of the smart curved beam, where the effect of piezoelectric material is also included. Here, in this case, the effect, the functionally graded material is considered titanium alloy and zirconia. Here, it is a mixture of ceramic and metal. This is another type of functionally graded material that is generally made of uh, effect variation in the effective material properties is due to variation in the composition. It is a mixture of two materials, zirconia and titanium alloy. Here the temperature dependent material properties are considered, and delta T is considered as 800 Kelvin. The curved beam, the first two modes of the frequencies are presented compared with the reference result for two different H by L ratios, and we found that there is a good agreement between the result as well as it converges at n is equal means number of elements is equal to 20. And here a comparison is presented for the smart functionally graded beam. Here I have took for the comparison purpose, I have considered a straight beam where we kept radius of the curvature is equal to infinity, as well as the thickness of the piezoelectric layer is 0.001 meter. And we found means we applied the voltage potential difference, 20 volt, 0 volt and minus 20 volt, and we compared our result with the existing results for various volume fraction index. So we found there is a good agreement between the results. And here the effect of applied voltage on the frequency parameters of the functionally graded beam is observed by increasing here three potential differences are taken, applied voltage are taken: 50 volt, 0 volt and minus 50 volt for various volume fraction index n is equal to 0, 0.5 and 10. Here we observed that on increase by applying the minus voltage, the frequency parameter is increasing from when it is means when there is no load is applied, no voltage is applied, means we have taken applied voltage V is equal to 0, then it has some frequency, and when we apply minus voltage, then the frequency parameter will increase. And in case of application of the positive means plus voltage plus 50 volt, then the frequency parameter decrease. Now moving to the vibration analysis of the nano beam. Nano beam, here the most important parameter is non-local parameter, which is mu, as we discussed during the modeling of this non-local theory. So in this case, I have considered a straight beam having H by L ratio, means length to thickness ratio is 100 as taken by Elther, as presented by Althar 2012, and we found our result is quite comparable with the reference result for various values of mu, that is non-local parameter, and these non-local parameter depends on the geometric as well as material property, various geometric as well as material properties of the nanostructure. This is another comparison where we have considered non-local parameters 0, 2, and 4, and the effective material properties are given here, and there I have considered hinged boundary condition, and the results are presented for various values of the volume fraction index. This volume fraction index n governs the composition of the ceramic and metal. Means for n is equal to 0, it's 100% ceramic and metal component is almost 0, and for n is equal to 1, it's 50% is ceramic and 50% is metal. So we found that for various values of the volume fraction index as well as various values of the non-local parameters, my results are very comparable with the reference result. Now we have observed the effect of non-local parameters on the first on the first five frequencies of the nano beam. In this case, I have considered a straight beam with H by L ratio is 100, and the effective material properties are given I have considered ceramic and metal. So for the ceramic, it's EC is equal to 390 GPa, and EM is equal to EM is a metal. The subscript C denotes the ceramic component as well, and the subscript M denote the metallic component. So the ceramic component and metal component, their material properties are taken as written here, and the boundary condition is simply supported, and this is the non-dimensionalized parameter to non-dimensionalize the frequencies. We have taken this particular non-dimensionalized parameter, and the result is presented for various non-local parameters, like we have considered 0 to 5, and we have also considered 5 different modes of the frequencies of this nano beam, and we observed that on increasing the non-local parameter, the frequency parameter decreasing with the increase in the non-local parameter, but it has significant effect for the higher mode, like for the fifth mode. When we increase the non-local parameter from 0 to 5, it is means the frequency get reduced by 73%, and for this first mode, it is around reduction in the frequency is around 18%. So for by observing by based on this result, we can conclude that the effect of non-local parameters also depends upon the mode of the frequency. Here, the effect of porosity on the frequency response of the functionally graded curved beam, frequency response of the nano beam with different values of volume fraction index n. Here, the ceramic and metal, the material properties of the ceramic and metal is given here, and the boundary condition is simply supported. And in this case, L by H ratio, that is length to thickness ratio, is 10, and mu, that is non-local parameter, is considered to be 1 into 10 to the power minus 12. So we found that in the results for the various volume fraction index as well as porosity coefficient, that is denoted by alpha. Here we consider two types of porosity distributions, even distribution and uneven distribution of the porosity. So in case of even distribution of the porosity, on increasing the value of n, the effect of porosity coefficient, that is alpha, is changing. Like for n is equal to 0, it's in the effect is increasing, means on increasing the porosity coefficient alpha from 0 to zero point 0.2, the frequency parameter is increasing. But for the higher values of n, volume fraction index, it is decreasing. But in whereas in case of uneven distribution of the porosity, on increasing the porosity coefficient and alpha from 0 to zero point 0.2, the frequency parameter is always increasing. Sorry. Here, the effect of various geometric imperfections are presented. The for this particular result, I have considered the geometric imperfection amplitude is eta is equal to 0.2, and for the perfect structure, it is geometric imperfection amplitude is 0. For various volume fraction index, the results are presented here, and we found that on increasing the imperfection amplitude, uh, the frequency parameter is increasing. But in case of G1, G2 type, its change is uh, means the effect is maximum in case of G2, and the in case of L2 type, the overall effect is minimum. Now moving to the conclusions. Irrespective of the porosity distribution types, the effect of opening angle depends upon the type of the boundary condition used. The frequency parameter always increases with the increase in the value H by L ratio. That is, from this particular statement, we can also further conclude that for the thin structures have higher frequency parameter than a thick structure. On that, on applying the minus voltage causes decrease in the frequency parameter, whereas the on applying the plus load, means plus voltage, the frequency parameter will increase. By increasing the volume fraction index, and the frequency parameter is decreasing. Why it is happening? As I have discussed, by increasing the value of n from 0 to infinity, the metallic content increases. For n is equal to 0, the ceramic content is maximum and metal content is 0. In case of 1, it is 50-50%, 50% ceramic and 50% metal. And after 1 to infinity, on increasing the values of n, the metallic content is constantly increasing. In compared to ceramic, the metals have lower elastic, means lower stiffness. So on increasing the value of n, the stiffness of the structure is decreasing. When the stiffness decreases, then the frequency will obviously decrease by increasing the volume fraction index n. The effect of imperfection is minimum in case of L2 type and maximum for the G2 type geometric imperfection. As the non-local parameter increases, the frequency parameter decreases, and the effect of this non-local parameter is maximum, means highest for the higher modes. Like as I have discussed, it was around 73% for the fifth mode of the vibration. Thank you. Any question? And I would like to acknowledge my guide, as well as my colleagues, Mr. Vikram and Shakir. And I am associated with the Computational Design Lab, present in the IIT Mandi. Thank you. Hello?
So, any questions from the participants?
Any questions with the participants, they can pose in the chat window. Hello. Hello, participants can pose the questions in the chat window. Sir, I'm audible?
Yeah.
Yeah, okay. So someone is asking, like, is there any experimental study through which you authenticated your data?
No, I have not compared my result with the experimental results, because experimental setup is not available in our IIT. And although I have compared with some uh, analytical results, and some experimental results are also available in the literature, and they have many other authors have compared their results uh, to validate their theories. Like they have published their theories, like non-local theory. So they have compared with the experimental results also. But in my case, I have not performed any experiment till now.
So which tool you have used for computations?
Uh, MATLAB and this uh, finite element method, and we have developed code in MATLAB, and then we performed the study.
Any other questions from the participants? So can we assume that there are no questions? Like, sir, if anyone is working in this area or want to share their experience, they can come forward and share, sir. Because today is the last day of the FTP. I request the participants also to share their experience or share their work.
And one more thing, if anyone have further query, he can contact with me via mail or any other medium. So we can discuss later also, anytime. Means I am ready to discuss with participants anytime.
Okay.
If you have time, then we can also present a small portion of the material stochasticity portion. Can I?
Yes, sir, we have time. You can present it.
Okay. I thought it will be late.
Okay.
So,
If you are willing to.
yes, ma'am. I'm willing.
The other quiz I'll be posting in the next session. You can attempt it.
Sorry, ma'am?
Yeah.
Sir, it's for the participants. Sir,
Yeah.
Prashant, sir, you have any doubt? Prashant Ragam, sir. So you have raised your hand. You have any doubts? Okay, no doubt. So you can proceed with
Oh, okay,
the.
ma'am. Okay, ma'am. Just a minute. Yeah. The manufacturing of the functionally graded materials is quite complex, and there is a chance of material discontinuity and that force inclusion in the structure is possible. So in that case, there will be randomness in the material properties. When there is a randomness in the material effective material properties, then there is structural response will be also uh, uncertain. So to consider material stochasticity, we get more reliable and accurate results for the structural response. For that case, I have used first order perturbation technique to model material stochasticity present in the structure. Here we use perturbation technique. So we used means we perturb the basically the basic governing equation of the uh, structure is it means eigenvectors. Eigenvalues are denoted with the capital lambda, and eigenvalue is small lambda, and k and m is the stiffness and mass matrices. We have considered randomness in each parameters. Then these parameters can be expressed as their deterministic part and some randomness in their part. So like stiffness is divided into two parts, uh, deterministic stiffness as well as randomness stiffness. Similarly, material matrix means mass matrix, eigenvalues and eigenvectors are also divided into their deterministic as well as their random part. by by putting these values in the parental equation, governing equation, then we get the two equations. By separating them with deterministic and non-deterministic part, we get zeroth order equation, that is completely deterministic equation, and first order equation. Here only one random part is associated with one term, and higher order terms like second order perturbation terms, like there is two random parts are product within a term. So I have neglected those terms. For the zeroth order equation, by solving the zeroth order equation, it also satisfies the orthogonality condition, means eigenvectors when it is multiplied with the mass matrices, transpose of the eigenvectors multiplied with the mass matrix, and then multiplied with the eigenvectors, we get delta, that is canonical delta. Kronecker delta. It is one for the I when I and j is equal to, it means I equal to j, and it is 0 for other values. And similarly, the uh, eigenvectors transpose of eigenvectors is multiplied with the stiffness matrix. Then it is giving eigenvalues directly. Here, any vector in n-dimensional space can be expressed as a linear combination of themselves. So deterministic part is added with the multiplication of the small change in that particular, means a small perturbation associated with those parameters, and by adding all these terms we get random eigenvector. By putting these random value of the random eigenvectors, we get the frequency parameter that is random. And similarly, this particular coefficient of Cij, this particular coefficient can also be obtained later on. And by here we assume that the material, means when we found there is a randomness in the particular structure, and we are using first order perturbation method. In this particular method, we obtained Taylor series. We applied Taylor series expansion to obtain some randomness associated with particular properties, like these properties are generally material properties, like Young's modulus and other. So these can be, means the effect of these particular material properties, how these material properties are means affecting the stiffness and the other parameters. So for this particular thing, we use Taylor series expansion along the mean values of those particular random variables, and we neglect, we just keeping first order terms and neglecting higher order terms. And the variance of the eigenvalues and eigenvectors can be obtained using this particular formula. And here I have to few results also.
So you're
Yeah.
sharing any slides, sir?
Sorry.
You're sharing any slides?
Yes, ma'am.
But your thank you slide is only visible actually.
Oh, now.
No, you have to close this.
Oh, now. Okay, okay. Now,
Yes,
is
sir.
it visible?
Yes, sir.
Okay. Okay. So I am presenting stochastic analysis of the functionally graded panels. Here we found here the comparison study is presented. Comparison as well as convergence study is presented for the standard deviation by mean, that is covariance of the present in the frequency parameter. When we assumed randomness in the material properties, like if very randomness associated with the ceramic component, that is Young's modulus of the ceramic and Young's modulus of the metal is 1%, and the randomness associated with the ceramic uh, and metal component densities is 1%, then the overall randomness in the frequency response is observed, and the effective values, mean values means that their deterministic frequency response as well as their stochastic component means their deviation uh, from the mean values is calculated, and we found that uh, by increasing the volume fraction means randomness, obviously the randomness in the response will increase, and for this particular case the randomness is 0.54% for n is equal to zero point 0.5, and we compared our result with the existing results. Those results are based on first order perturbation method as well as random factor method. And one more thing here. Here we consider the randomness in the density only. Uh, Means by fixing the randomness in the density is 1%, and we increase the randomness in the Young's modulus of the ceramic. By increasing the randomness in the ceramic, the randomness in the frequency response is also increasing. And for different H by L ratio means for H by L ratio is equal to 0.1, it is maximum, and it is minimum for the 0.02. So the how here I am presenting the how the randomness in the particular one material means one particular component of the material is affecting significantly the overall response of the structure. So I am concluding with this particular remark by we should also consider the randomness in the each particular material properties so that we can get more optimized means more robust design for the particular structure. Thank you. Okay, ma'am.
Yes, sir. Hello.
Yes, ma'am.
So we are concluding, sir. Hello.
Yeah,
I didn't get it.
I have concluded my
Okay,
presentation.
okay.
Just finished.
Thank you very much, sir, for your valuable time. And
Thank you,
the
ma'am.
participants, any questions you can post because it's his sir's personal work. Anyone who's working in that area. You can unmute yourself and speak.
Okay, thank you, ma'am.
Okay. Uh, so thank you very much for your valuable time, sir.
Okay,
So this has been, I mean, today is the last day for the FDP. I mean, we have one more session with Jose Manuel, sir. The
okay,
thing is, still we have the participants who are coming regularly. It's been
okay, okay,
2 long weeks, and with the cooperation of speakers like you, we could successfully come to this. Thank you very much for your
okay.
time, sir.
Thank
On
you.
behalf of MLR Institute of Technology and Department of Aeronautical Engineering, I wholeheartedly wish to continue this association in future as well.
Okay, okay. Thank you, ma'am.
Thank you, sir.
Any formalities from my side? Can I close?
Yes, sir. I'll mail you for the remaining things.
Okay, okay, ma'am. Can I close?